Hey, this is Mr. A, and we have been exploring, and so now it's time to do some explaining. You have been brainstorming about questions that you would have to have answered in order to build a scale model of the Earth and the Moon. How big is the Earth compared to the Moon? What materials can we use? How do we position the Earth and the Moon? How big is the Earth and Moon in real life? How far away is the Earth from the Moon? What is the scale factor? If you had the answer to all these questions, then the project would not be very hard, would it? So let's get started. If you haven't already, stop the video and set up your page for taking Cornell Notes. Don't write down these main topics right now, but I just wanted to give you a little heads up. These are the three main topics that we're going to be talking about in today's lesson, scale modeling. We're going to be talking about standard SI measurements, scientific notation, and scale factors. First of all, I need to cover some really basic information, just so you know. Standard SI measurements, SI stands for the International System of Measurements, and it's basically the metric system in which the meter is the standard unit of length. Length can be used to measure the distance between two objects or the diameter of an object. The diameter is the edge-to-edge distance of a round or spherical object. The second topic is scientific notation. Now this is a pretty big topic, just like the metric system is, but I'm going to give you just what you need to know in order to do the project. And I think the best way to learn about scientific notation is to do lots of examples. So let's get started with our first example. If you started your project and you Googled distance between the Earth and the Sun in meters, Google would show you this. Now, that's what we asked Google, and Google gave us the right answer, but that's not very useful if we have to do math. So we need to either expand that number or we need to write it in scientific notation. Scientific notation is really compact because there's only one digit to the left of the decimal point. But we still need that to represent a really big number, so that's why we multiply it times 10 to an exponent. In this case, the exponent is 11. This exponent tells us that what we've actually done is moved the decimal place 11 places. Let me show you. In expanded form, here's 150 billion, and the decimal point's right there. If we move the decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we move the decimal point between the 1 and the 5. Now, 1.5 is not 150 billion, so that's why we need to multiply it times 10 to the 11. Maybe this will make sense if I show you another example. Example number 2 is the sun's diameter. If you were to Google what is the diameter of the sun in meters, Google would say that it's 1.4 billion meters in diameter. In expanded form, that would be, and in scientific notation, that would be the 9 exponent tells us that we've moved the decimal point 9 places. This will be my last example, and I want to do it a little bit differently. If you were to Google the diameter of the Earth in meters, Google would say that the Earth is 12.742 million meters. If I write that in scientific notation, it would look like this. Again, scientific notation requires that you have only one digit to the left of the decimal. Now that makes this a very small number, but it's big because it's multiplied times 10 to some exponent. And that exponent tells us how many places we have to move the decimal point. So if I write this in expanded form, and I move the decimal 7 places, fill in the zeros, you can see that this number is, if we put in the commas there, 12,742,000. If this seems like it's hard for you, just write down the examples and we're going to do lots of practice in class. The next thing I want to talk to you about is scale factor. Scale factor is the ratio of the measurement of the object in the real world to the measurement of the object in the scaled world. And if you would write that as a mathematical expression, this is what it looked like. Scale factor is equal to measurement of the object in the real world divided by the measurement of the object in the scaled world. So again, I think the best way to learn this is to do some examples. The first example I'll use is Matchbox Cars, or Hot Wheels, those little cars you used to play with. They're about that big. You know that real cars, well, they're much bigger, right? Let's take an example of a real car, which is about 4.6 meters. From bumper to bumper. If you would take that same car and make a Matchbox car out of it, the Matchbox car would be about 7.5 centimeters, or 0.75 meters. So the measurement of the car in the real world, 4.6 meters, compared to the measurement of the car in the scaled down world, 0.075 meters. If you would do this division, then you would get the scale factor, which would equal 64. So Matchbox cars are 1/64th scale. Now I want to do another example of scale factor using scientific notation. Because, well, after all, in the project, you're going to have to be scaling down really, really big objects, which are represented by their length in meters expressed in scientific notation. So we're going to have to do some math with scientific notation. So I better show you how to do that. Let's just take an arbitrary example where you've got an object, say, that is, I don't know, 7 times 10 to the 3 meters in length in the real world. And then you want to scale that down so that in the scaled down world, that object is 3.5 times 10 to the 2 meters in length. Just like you did before, you would do this division. But if you haven't divided numbers like this before, it might be a little scary. I'm not going to ask you to do this by hand. I'm going to ask you to do it with your calculator. I'm going to show you how to do this on a TI-84 calculator, which is a calculator that a lot of students have. The first thing I'm going to do is I'm going to put my calculator into scientific mode, because after all, we are in science class. Now the question that we had was the division of 7 times 10 to the 3 divided by 3.5 times 10 to the 2. There's lots of different ways to enter this in your calculator, but let me show you how I do it. I'm going to enter 7, and then the times 10 to the 3, I'm going to use this the EE function. And I think that stands for engineering or exponent. I'm not sure, but it's the second function of the comma button. So I've typed 7, and then I'm going to go EE to the 3. And I'm going to divide that by 3.5, and again, EE to the 2. So the E in the display is representing times 10, and then the number that follows is the exponent. So I've typed it in, and if I hit enter, then I get my answer back in the same kind of notation, 2e to the 2, which means 2 times 10 to the 1, which is 20. So the answer to our scale factor example number 2 is 20, or 2 times 10 to the 1. This is my last example of scale factor, and it's going to be more typical of what you're going to have to do for the project. What scale factor would be required for modeling the distance between the Earth and the Sun such that the model would fit in our classroom? So what would you have to know? Well, you need to know the distance between the Earth and the Sun, and then you need to know the size of our classroom so that the object, the distance, in the real world would fit in our scaled down world. The Earth-Sun distance, remember, is 150 billion meters. The size of our classroom is 5 meters. So you think you can calculate a scale factor? It'd be 150 times 10 to the 9 divided by 5. Try that on your calculator. That's a pretty big scale factor. So that's my explanation of scale modeling. I'll see you back in class when we can practice it.